Welcome back to the continued classes on plastic analysis of structures. So in the last class we had begun solving few examples to determine the ultimate load carrying capacity of the structure. So what we learned is that if the structure is a determinate structure, it's very easy. A determinate structure has the fixed bending moment diagram. A determinate structure whose bending moment diagram is known shall undergo collapse by the formation of just one plastic hinge, and the location will be where we have the maximum bending moment diagram. So this is very much certain in the case of a determinate structure. All we have to do is that determine the bending moment diagram from elastic analysis and equate the maximum bending moment anywhere in the structure to the plastic moment capacity of the section, which can be determined from the yield stress and the cross-sectional details, and this gives us the value of the ultimate collapse load. However, when we shift from determinate to indeterminate structure, then complications they start coming in the analysis. So in the case of an indeterminate structure, more than one hinge would be required, and the formation of these hinges is sequential. We have to determine which will be the first hinge and which will be the second hinge, and so on. For example, this structure, we know that two hinges will be formed. So where will be the first hinge formed? The first hinge will be formed at location which has the higher bending moment. So we have to do elastic analysis and find out that and equate the bending moment at that location which was A to the plastic moment capacity of the section. So this gives us the load at which the first plastic hinge will form, and then we have to carry out incremental analysis for a modified structure, because once the first hinge is formed, the structure is changed, and then we have to find out the incremental load that will lead to the formation of the second plastic hinge. So once two plastic hinges have been formed in this particular structure, which is a prop cantilever structure, the structure can be deemed to have failed. Here we also saw that in the case of determinate structure, till the yield point we have a straight line, and after the yield point the curve comes, because the section is no longer undergoing elastic deformation after the yield stress, and it undergoes curve, and finally when it reaches the plastic moment capacity, because the curvature becomes infinite, so we get a straight line after that. In the case of the prop cantilever, the indeterminate structure, we have bilinear curve till the occurrence of the first yield point. And if, for example, the indeterminacy is n, the initial part will have n different linear regions. So here also the curve starts the moment the yield point is reached at the second hinge location, and after that the curve attains a straight portion when we reach the plastic moment capacity, and because the curvature is infinite, so we get infinite deflection at that point. Now in the case of the prop cantilever, what we found that at the ultimate collapse, the bending moment at the two hinge locations would be just equal, and the value shall be equal to the plastic moment capacity of the section. This gives us some intuition to find out an easy and an expedient method, a faster method, which does not involve solution of an indeterminate structure. So we'll explore this today. Now finally, when we go further to, if we increase the indeterminacy of the structure further, then we have more tedious procedure. For example, here the degree of indeterminacy is 3, so 4 hinges shall be formed. However, what are those 4 hinge locations? That we shall know only if we resort to this kind of sequential analysis we form hinge after hinge. One by one we do analysis, of course elastic analysis of the structure. First we have the original structure and we perform its elastic analysis, and we find out where is the location of the highest bending moment. That will be the location for the first hinge. And similarly then we do the incremental analysis and then find out by the superposition where the structure has the next highest bending moment, and that gives us the location of the second hinge, and so on. We go further. So here the problem is that we cannot predict immediately the hinge locations. In fact, here if we see the peaks, so peaks are the possible hinge locations. So there will be 4 hinges, but there are 7 possible peak locations where hinges could be formed. So it's very difficult to just identify those 4 locations by inspection. So what we are proposing is that we will use a faster method. The basis will be that at the final collapse, the bending moments are equal to the plastic moment capacity of the section at the key locations. And how do we find those key locations? We'll use some kind of intuitive guesswork. So there are 2 ways to achieve this. One is the equilibrium approach and other is the principle of virtual work. We'll see both of them and we'll solve the structure, the prop cantilever structure, which we have already solved before, and we had got the final value of the ultimate collapse load also, 6 MP by L. So that we'll solve again by the equilibrium approach and we'll compare the answer. So in the case of the equilibrium approach, we make use of the fact that at the final collapse, the bending moment at the hinge locations shall be equal to the plastic moment capacity of the section. So here what we need is we need to obtain a qualitative shape of the bending moment diagram. We don't need to obtain the exact elastic bending moments, their values at various locations of the structure, but we just need to guess the shape of the bending moment diagram, and then we make use of the fact that at the ultimate collapse load at the plastic hinge locations, the bending moments will be equal to the plastic moment capacity of the section. So here we have identified that A and B, they are the possible hinge locations because they are appearing as the maxima in the bending moment diagram. So what we do, we consider equilibrium of the structure when it's at the verge of collapse. Verge of collapse means that the load is increased gradually, and when it's just about to undergo failure, we are observing the equilibrium of the structure. Okay, so here the load is just an iota smaller than the ultimate collapse load, because if we increase it to the ultimate collapse load, you will not be in position to observe the equilibrium of the structure because the structure would have collapsed. So we are deliberately limiting the load to just an iota smaller than the ultimate load. So at that particular instant, the bending moments at both A and B shall be equal to the plastic moment MP. So now at this stage we just consider equilibrium of the right part BC. So we deliberately cut a section of the structure exactly to the right of the point B. So we just observe BC, and now when we have drawn the free body diagram, we draw here the bending moment also equal to MP, because we know that this bending moment shall be sagging type. So what we see here, that here we have the reaction RC, and at point B we have the shear force on the BC part of the structure. So now what we do, we try to find the value of RC by considering the moment equilibrium. So all we have to do is we take moment of the forces about B, and by this we obtain the reaction RC. Once we have the reaction RC, now we consider the overall equilibrium of the structure. So we have drawn the free body diagram of the entire structure now, and by vertical equilibrium we can find RA, and once we have RA, then the sum of RA and RC shall give us the ultimate load. Or alternatively, we can consider the moment equilibrium of the entire section about A, and once we do this, then we'll get the value of the ultimate load directly. So this is coming out to be 6 MP by L, which is same as the one computed by the previous analysis. The difference lies here that unlike the previous solution where we had to solve one indeterminate structure and the other determinate structure for the incremental analysis, that is we had to solve two different structures, here we don't need to do those tedious calculations. But another difference is that in the first approach we knew where the first hinge will be formed and where the second hinge will be formed. Based on the actual analysis, we had come to the conclusion that the first hinge will be formed at A, followed by the hinge at B. Here we are not in position to know which hinge shall be formed first and which hinge will be formed later. So here the sequence of hinge formation is not there, and generally we don't need also. However, the method is very expedient. Let's now see the virtual work approach also. So here we have made use of this to avoid solving indeterminate structures. Now in the virtual work method we use the principle of virtual work. Earlier what we have been saying is that we apply a virtual load and the virtual load rides along the real displacement. Now here what we'll do, we'll apply a virtual displacement, and the real loads, they ride along the virtual displacements and they do virtual work. So we again equate the internal virtual work with the external virtual work. So here assumptions are that the structure is just at the verge of collapse, so the load is just an iota smaller than the actual failure load, and secondly, the geometry of the structure does not change as a result of the plastification. So that is, the structure does not have any geometric non-linearity. So here we have applied the load and the structure is just at the verge of collapse, so there will be two plastic hinges A and B, which we can ascertain from the shape of the bending moment diagram. So at both these locations the bending moment shall be equal to MP. Now at this particular condition we apply a virtual rigid body rotation theta in the structure. So that's how we have applied the rigid body rotation theta at A. So as a result of this, the structure undergoes this kind of profile. So we have applied the rigid body rotation at A. So it's a rigid body rotation, that means there is no bending of the parts. Hence the internal virtual work is done only by these plastic moments, and it's not done by the internal bending moments of the parts. So the internal bending moment within the two parts AB and BC, they are not involved in any virtual work. So after this we just equate the external virtual work with the internal virtual work. What's the external virtual work done? The applied load P, it comes down, and by how much amount it comes down? Because here the rotation angle is theta and this length is L by 2, so it comes down by L by 2 into theta. So here the external virtual work can be written like this. And what's the internal virtual work done? Internal virtual work is done at two locations, at A and at B, and the work is done by the plastic moments over there, because these plastic moments, they ride along the rotations which are virtual in nature. So at A we have the work done equal to MP into theta, that is the moment multiplied by the rotation, and at B we have added 2 theta. Now why we have considered 2 theta? Because at B the rotation will be double. The rotation will be because of the parts A, B and BC, so the net rotation at point B is 2 theta. So we have already understood why only MP does the internal virtual work and not the bending moments because here we have applied rigid body rotation. So there is no relative bending in anywhere in the structure. So by solving it, the same answer equal to 6 mp by L. So whether we use the virtual work approach or we use the equilibrium approach, we are able to save our time. But of course, we are not able to tell the sequence of the hinge formation, and that is not very important also. So now, which method would you think or would you judge as the best out of the three methods? The first method, the longhand method, where we do sequential analysis, where we also know the sequence of hinge formation, so that's very tedious. And of course, now in between the virtual work method and the equilibrium approach, you have to find which is better. Now if we try to apply these shortcut approaches on a complicated structure, then we have to bring about few more modifications in the procedure, because the procedure will not be as simple here. For example, this structure which we have considered before also, here the degree of static indeterminacy is 3, so 4 hinges will be formed and there are 7 possible hinge locations. So which of these 7 locations, which 4 are going to be the actual hinge locations, that is something which we don't know at the beginning, and we are not going with the sequence of hinge formation, so we have to apply some kind of guesswork. That's why we'll now formulate a procedure that will consider an intuitive engineering guesswork followed by the use of 2 theorems, and that will help us in getting the solution with ease. So what are these theorems? There are 2 theorems of plastic analysis, and before that we just see the assumptions. Assumptions is that at the point of the collapse, the loading system is not affected and the geometry of the structure is also not affected. That's the structure does not have any geometric nonlinearity. So the first theorem is the uniqueness theorem. So the uniqueness theorem states that following conditions must be satisfied simultaneously at the point of collapse of the structure. Number 1, equilibrium condition must be satisfied. That is, all bending moments, they should be in equilibrium with the applied forces and reactions. So this is very natural and easily understood that equilibrium condition must be satisfied. Then the yield condition, which states that at all points of the structure the bending moment should always be less than the plastic moment, and this is also understood. Basically this fact will be used to make checks, because we'll be making use of some engineering guesswork, and after that you will do this check to ascertain that our guess is correct. And then the third is the mechanism condition, that there should be sufficient number of plastic hinges formed so that the mechanism condition results. Now this uniqueness theorem will be breaking into 2 parts, the upper bound and the lower bound theorem. So the mechanism condition, we will basically make it an upper bound theorem, and the yield and equilibrium condition, they will be clubbed into a lower bound theorem, as we'll see from the next slide. So the upper bound theorem states that if we can find loading such that a mechanism is formed, that is, we do a calculated intuitive guesswork. For example, in the multi-span beam, we found that we have to choose 4 hinge locations out of the 7 possible, and there will be a number of combinations. So all those combinations are possible candidates of the failure mechanism. So the upper bound theorem says that if we are able to guess some mechanisms, then these are the upper bound. That is, the failure loads calculated for all these mechanisms, they will be on the higher side of the actual ultimate load. Then we have the lower bound theorem. So lower bound theorem states that if we are able to find a distribution of moments such that the equilibrium and yield conditions are satisfied, then this would imply that the structure is either safe or at the verge of collapse. That is, the load shall be on the lower side of the ultimate load. So naturally, now if the upper bound and the lower bound theorems both are satisfied, then we will have the condition that the load shall be just equal to the ultimate collapse load. So we will continue from here. In the next class we will formulate a procedure which we will apply, and then we will solve some examples. So after this session, you are all invited to come at our MS Team channel for further discussion and for doubt clearance. Thank you very much.